Welcome everyone and hi. So I will continue from the previous lecture part 2. Okay, I try to finish it this record for the whole part 2. Okay, so I'm going to share the screen right now. We stop at this slide. Okay, so kita continue this one. Okay, so adiabatic operation for PFR or PBR. So the guideline or algorithm to solve problem for adiabatic reaction in a tubular PFR or PBR reactor is clearly given in table 11-2. Okay, so you can have a look at the right side of this slide. Okay, whereby assume that we have a gas phase reactions and it is a reversible. Okay, and is carried out in a PFR in which pressure drop is neglected and pure air enters the reactor. Okay, so start with the more balance. Okay, so this is the design equations for the PFR. Okay, dx over dv is equal to negative RA over FA naught. Okay, so the red law would be negative RA K times CA minus CB over KC. Okay, whereby you have to get it from the RA net. Okay, for forward and also for the reverse. Okay, which equals to negative KFCA plus with the KRCB. Okay, so the negative RA net, okay, make it as negative for the RA net is equals to KFCA minus with the KRCB. Okay, whereby KC is defined as KF over KR. Okay, so rearrange the equations and you will get KF times with the CA minus CB over with the KC. Okay, so the K, direct constant, is equal to these Arrhenius equations, and for delta Cp is equal to 0 because this is a pure feed. Okay, and Kc, all right, so this is a direct constant for irreversible, and this one is for reversible. Okay, so for the reversible we have a delta Hrx here. Okay, so for the gas, the epsilon is 0 since it is a pure A enters, and P is equal to P naught, okay, because it's neglected. Alright, so the stoichiometry would be Ca is equal to Ca naught 1 minus X T naught over T. We cannot cancel this one because this is non-isothermal. Okay, there is a temperature changes. Alright, then Cb, alright, the product, this is the reactor, kalau forward lah, and then this would be the product is equal to Cb is equal to Ca naught X T naught over T. Okay, so you combine this one, okay, the red law, and also the K, okay, you will able to get these equations. Okay, so negative RA is equal to Kc A naught. Alright, so what is Kc? Kc is defined with T11-24 and the small k here represented by T11-23. Okay, so you don't have to put k ni dulu lah sebab it's too nanti lengthy here. Alright, so just replace with the just put it as Kc dulu dengan k biasa dulu. Okay, this is just rearrangekan dia, masukkan Ca dia, Ca naught 1 minus X, and Cb dia lah Ca naught X. Okay, over Kc. Okay, just replace dengan this. Okay, this one masuk kat sini, and this one is this one. Okay, so to relate temperature and conversions, and we apply the energy balance to an adiabatic. If all species enter at the same temperature, means that Ti naught is equal to T outlet. Okay, T inlet is equal to T outlet. Okay, so assume that Q is equal to 0 because this is adiabatic, and W, there is no work shelf, so it's equal to 0. Then you will have this equation. Okay, so this equation from equation 11-29, okay, from the energy balance. Okay, whereby the delta Cp here is equal to 0, since it is a pure feed enters. Okay, so you just take it out, the T naught here. Okay, rearrange it and you will get this one. Okay, so this one you can solve it lah. Just put it the value of delta X, and then T naught, T enter, and CPA you will get the T temperature. So this is the guideline or algorithm to solve problem for adiabatic reaction in tubular fluids given in table 11-2, table 8-2A. Okay, same like previously. Okay, whereby this one you can take it out. Okay, define CA not ni pun CA. Right. Also, you can make it as CA is equal to FA V. Alright, FA naught 1 minus X. Okay, then we have a V naught 1 plus epsilon X. Okay, P over P naught over P, and then T over T naught. Okay, so this one, you cancelkan, this one also cancel epsilon 0. Okay, so that's why we have a CA naught 1 minus X T naught over T. Okay, this is how we get it. Okay, I lupa nak terangkan tadi. Okay, so this T actually, alright, is depending on this equation. Okay, which is you will use this one. Okay, so T this adalah daripada energy balance. Alright, so equation T11-21 through T11-29, okay, can easily be solved using either Simpson rule or ODE solver. Okay, this is kalau you nak dapat ni lah, the profile of the concentration. Okay, so moving on. Okay, so the adiabatic PFR, PBR design as described in the algorithm in previous slide can be solved by two ways. Okay, whether you can use numerical method, okay, Simpson's rule, okay, when you want to get the V, or by using an ODE solver, for example, from Polymath or MATLAB. Okay, this one you akan learn nanti after this topic. Okay, so let's say we have this is the volume for the PFR. Okay, so first you have to choose X, and then you calculate T, and then calculate K, and then calculate negative RA, and calculate the FA naught over negative RA. Okay, so this would be the sequence. Okay, because look at this equation first. Okay, we don't have the value of the FA naught over negative RA, so we have to do it backward. Okay, so negative RA kita dapat dari mana? So negative RA is related with the K. Just now is K CA naught, okay, times with the 1 minus X, okay, minus with the X over XC, over KC, okay, times with the T over T, T naught over T, okay. So in order for you to look at this equation, okay, so you don't have the T, okay. So this T, how you get it? It will relate back to the Arrhenius equation, okay, whereby K is equals to using this equation. Okay, so once you put the value, you know the value of the, what do you call it? The T, okay, you can get it from the equation this one first, okay, the T, okay. So daripada situ T, you dapat pula nilai K, okay, because the T relate with the K, alright. So and then how you need to use the T here, okay, you need to get the information of X, okay. So daripada mana kita dapat X dia adalah kita kena set mula-mula X equal to 0, okay. Because we want to make it from 0 to X something, X3, okay. So this is a step, set x to 0 equal to 0. Lepas tu calculate T using the energy balance. Okay, tadi I cerita yang kalau nak tengok backward dia lah. Okay, and then once you get the T, you will be able to calculate the K sebab K is related with the T, temperature, Arrhenius equation. Okay, and also Kc ni pun you boleh calculate once you have the T here. Okay, and also the delta HRXC which you have to calculate it. Okay, so usually dia akan bagi initial value of this one lah. Okay, dekat T2. Ni T1, ni T2. Okay, so and then after that you calculate the T0 over T. Okay, so you can calculate T0 over T by using this one. Okay, T0 over T adalah sebab apa you guna T over T0? Sebab you akan guna ni untuk negative RA. Okay, sebab dalam negative RA kalau you perasan there is nisbah T0 over T. Okay, so just put the initial temperature here and then T according the one that you obtained before. Okay, sebab benda ni adalah sequence. Okay, alright, so dapat T tadi kan, masukkan sini. Okay, so you will be able to get the negative RA. Okay, so make it as FA0 over negative RA. Okay, so this one will have different for x equal to 0 and then x equal to 0.1, x equal to 0.3 and x equal to 0.4. Okay, so you will have a different value. Okay, so you will apply the numerical method. Okay, is it 3 Simpson, or is it a 5 quadrature formula or trapezoid? Is based on how many function you have this. Okay, so for example, if you have 4 ni sesuai untuk 3 Simpson rule lah, 3 over 8 Simpson rule. Okay, in order for you to get the volume of the PFR. Alright, nanti kita akan buat this question exercise at the end of this slide. Okay, and then we have another method, okay, which is using the differential equation. Okay, this one you need to use a software. Okay, you cannot do it manually. Okay, in order to get the V. Okay, so this part is this one is the one that you can calculate lah. Okay, yang lain ni kita akan simulate sebab dia ada dx over dv. Okay, so dia boleh solvekan terus dx over dv. Okay, this is what we call as ordinary differential equation. Dia perkan something. Okay, like ds over dt, dp over dt. Okay, so this one you have to do in ni lah MATLAB or polymer. Okay, so this one I don't have to terangkan and this would be later on after this topic number 7. Okay, so okay, let's see some example here for adiabatic and reversible. Okay, this is example taken from the formula. Okay, we have a NC4H10 and IC4H10. Okay, isomerization take place here. Okay, so it is given a specific reaction, alright, K at temperature 360 K. Calculate the PFR volume necessary to process 100,000 gallon per day. Okay, this is the value when converts to kilomole per hour at x equal to 70% of a mixture of 90% mole and butane and 10% of pentane, which is the inert. The feed enters at 330 K. Okay, so it's already given the delta HRX at TR, okay, which is negative 6900, and given also the CP and B. Okay, this is for the what do you call it, the reactant pentane, and then this is the inert. Okay, ini butane, ini pentane. Alright, this inert. Okay, so activation energy is given and also the value of Kc at specific temperature of 60 degrees Celsius and also the Ca0 9.3 gram per mole over decimeter cube. Okay, so basically same again what you need to do. Okay, so this is A reversible to B. Okay, directions. So at equilibrium, remember at equilibrium the negative RA should be equal to 0. Okay, so this is the one that you need to derive in. Okay, you can start from the RA net lah. Okay, which is RFA plus with the RRA. Okay, then you need to make it as 0 here equals to something here. Okay, so at this case, when you set it RA to equal to 0, the KC will become equals to KE. Okay, dia dah jadi equilibrium. Okay, so from here, you dapat daripada ni lah, which is KE is equals to CBE over CAE. Okay, ni previous topik ni ada belajar. Okay, so just substitute what is CAE. So CAE is equal to CA01 minus EXE. So CBE, this is product. So CA0 times with the XE here. Okay, over KE. Alright, so you can cancel this one. Okay, rearrangekan dia in order to get a XE at the left side is equal to something. So equal to this one. Okay, so what is KE? So KE is represent with the equilibrium constant. Okay, which relate to the heat of reactions. Okay, dengan T. Okay, so kalau ada not ni maksudnya means dia refer dekat TR. Okay, so for CP, remember this is pure. Okay, masuk. So delta CP is equal to 0. Okay. Alright. So equilibrium conversion XE, the highest conversion that can be achieved in reversible reactions is, okay, so we have a XE here. Okay, so XE equal to KC, 1 plus KC. So substitute the value of the KE here. Okay, KE atau KC sebab dia sama je sekarang ni. Okay, so masukkan dia and then you need to plot K versus with the T. Okay, so once you vary the T here, value of T, you will have a different K value. Okay, so it depends lah sama ada kalau dia if it's endothermic, the curve is increasing. Okay, as the temperature increase. If it's exothermic, the K decrease as the temperature increase. Okay, but for XE, okay, it is opposite trend with the previous graph, whereby the endothermic, the XE increasing towards the temperature, but the XE decrease as the temperature increase for the exothermic reactions. So for endothermic reaction, the equilibrium conversion increase with increasing temperature up to maximum of 1 only, okay, because the limit for conversion is 1 only. For exothermic reaction, the equilibrium conversion decrease with increasing temperature. Okay, so that's the analysis from the graph. Okay, so exothermic is delta H is negative. Okay, so we have a, remember this is for adiabatic, so Q akan equal to 0, W is equal to 0. Okay, so this adiabatic temperature conversion relationship. Okay, so if you can see as the temperature increase, okay, for isothermic, the conversion of the energy balance increase. Okay, applicable to all type of reactors. Okay, and then we have a XE from the equilibrium, which is XE equal to KC over 1 plus KC ataupun KE. Okay, so it will goes downwards like this. Okay, so actually XE ni macam mana benda ni adalah depends on juga. Macam tadi kita tengok adalah A to B. Okay, maybe kalau A plus B, A plus B equal to C plus D, dia akan berbeza lah ikut pada equation tu. Okay, so here this is the XE. Okay, this is XE punya graph. Okay, daripada equation ni. Okay, I letak nombor 3 lah. This is one nombor 3. Okay, this is number 1, number 2. Okay, then we have a number 2. Okay, XEB. So XEB is selalunya yang menegak ni lah. Okay, so this is XEB, number 1 punya. Alright, so how do you get the temperature? Actually, is by using the equation of number 2 here. Okay, alright. So graphical solution of equilibrium energy balance equation to obtain the adiabatic temperature and adiabatic conversion of XE. Okay, so if the entering temperature is increased, okay, so if you can see T0 increased to TO1, right, as it goes further to the right side, okay, the energy balance line will be shifted to the right. Okay, so this is the energy balance line and straight line. Okay, so they will shifted to the right and be parallel to the original line. Okay, yang penting dia akan parallel lah. The parallel, okay, as shown by the dashed line. Alright, so this shows that this is a new XE, alright, B for T naught more than T0, okay, which is the increase. Alright, this is for applicable for exothermic. If in endothermic, okay, usually kalau endothermic pula, XEB akan menurun. Okay, opposite with the exothermic. Alright, so this is the one that you see. Okay, so this is the line for XE. Okay, XE, this one, and for the straight line, okay, with a negative slope, actually is referring to the from the energy balance here. Okay, XEB. Okay. So this one is a, sebab dia tak ada plus delta CP, sebab delta CP is equal to 0 sebab pure yang masuk one compound aja. Okay, so T, nak dapatkan nilai T ni, you kena ni lah varykan X dia. Okay, the one that I told you lah, kita ada T, kita ada XEB, and then we have a XE. Okay, so XE pun KC ni dia akan berkaitan dengan T kan, so that's why dia akan berubah. Ni pun ada kaitan dengan T kan, that's why dia akan bergantung pada mana yang you set T tu lah, berdasarkan yang ni you masukkan. Okay, kalau X berubah. Okay, so maximum conversion in adiabatically exothermic reaction can be determined using below equation. Okay, so this is the equation lah used for XEB. Okay, so the inlet temperature increase, the adiabatic equilibrium conversion decrease. Okay, this is kalau you tengok, ini kalau temperature increase, tapi tengok even though the temperature increase, tapi dia punya XE akan menurun. Okay, lagi ke bawah. Okay, so summary. Adiabatic CSTR, PFR and batch and PBR achieve this. Okay, so this SEB is equal to theta I CPI T minus C naught over delta H RX TR. Okay, so this is the one that kalau A to B. Okay, so gantikanlah, this is CPA. Okay, this is for reactant A only. Okay, kalau dia ada B, which is contoh A plus B, you kena consider lah this plus bit C, P, B, T minus T naught. Lepas tu sini kena ada plus delta C, P, T minus T R. Okay, tapi in this case sebab dia pure, so dia dah tak ada benda tu. Okay, so this is the equation lah. Okay, so this is XE, KE ni, then how do you get the T lah. Okay, T ni rearrangekan balik daripada sini. Alright, so curve A, this is the curve A. At a very low feed temperature, the specification rate will be small, that virtually all of the reactant will pass through the reactor without reacting. Okay, kalau very low feed temperature. Tapi as the feed temperature increase from a very low value, the specification will increase, as will the conversion. Okay, so kita nak tahu balik benda ni, trend ni balik apa, kita tengok pada benda alah ni. Okay, so the conversion will continue to increase with increasing feed temperature until the equilibrium conversion is approached. Okay, dia akan approach kat satu point ni. And then further increase in feed temperature for this isothermal reaction will only decrease conversion. Okay, so dia akan naik kepada satu point. Alright, so when it reach equilibrium, okay, especially bila dia touch the XE dengan XEB ni, dia akan turun balik. Okay, decreasing the equilibrium conversion. So reaction rate very rapid. Kalau B pula, dia very rapid. Virtual equilibrium reach in reaction conversion detected by equilibrium conversion. So ini dia turun sahaja. Okay, so this is XE lah, just menurun. Okay, so this is some exercise. Okay, I think I stop here lah. This I will maybe discuss in the synchronous class. Okay, thank you everyone.